So if I want to square this binomial, a plus b squared, or anything squared, is just that thing times itself. So this is really saying the same as a plus b times a plus b. That's what the squared means. That's the definition of it. Okay. Well, if I used our strategies from yesterday, we'd say, let's make a chart and multiply this stuff out. So I have an a plus a b. Got an a plus a b. So when I multiply this out, I get the following. I get a times a is a squared. A times b is, well, ab. A times b is also ab. And b times b is b squared. So we get this. You get a squared plus ab plus ab plus b squared. I see two like terms. These things in the middle.
AB squared.
What's in the middle? What's ab plus ab? It can't be squared because that would mean there's a multiplication in here. We only change exponents if there's multiply. So Brendan? Two of them. Our formula is this. What does this actually mean then? Since I used all variables here, it didn't matter what the heck this was. These could be numbers, these could be x's, they could be y's, this could be a 4, this could be anything. What it's saying is if you start here and you have something plus something else squared, you could skip all this junk in the middle and go directly to take the first term and square it, take the last term and square it, and in between take 2 and multiply those two things together. It's saying that this, if I want to multiply it out, I could go directly to this pattern. Okay? You don't need to multiply this out. You don't need to make a table. You don't need to combine all these like terms. You could go from here to there. And that's the point of today. Is to recognize that when I start in this situation, that I can go directly to my answer without the stuff in between. It's because of this setup. Okay. Let's see an example of it real quick before we do this, before we kind of see its partner. So if I have x plus 4 squared, what this pattern here says is that I could take, instead of writing this out, multiplying everything together, and then combining like terms, what I could instead do is do it much quicker. And I could say this is the sum of two terms being squared. This is a binomial being squared. So I could take the first term and square it. So I could take x and square it, plus twice of the first term, which is still x, times the second term, which is 4. And I could add on my last term, or my b squared. Notice that x and b, b, b. Simplifying this, x squared is x squared. 2 times x times 4 is 8x's. 4 squared is 16. Its partner, the complement to this, is what if I change the middle addition sign to a subtraction sign? Okay. If you do that, I claim that the pattern itself doesn't change terribly. And if we want to write it out, you could say a minus b minus b. If we use our table again, we get a minus b. You get a minus b. And if you multiply them out, you get an a squared again. You get a minus ab, another minus ab. Minus times a negative is a positive. I claim that if you change the sign in the middle, that the formula doesn't change a whole lot. In fact, what's the only thing that changes if I change the middle to a minus?
What terms?
You know, the middle term is now just negative.
Why is it negative b squared? Oh, because it. That's two questions.
A times negative b and a
No,
times
I mean,
negative.
like in the final. Why is it negative 2?
Because there's two of those. So I have a negative 1 and a negative 1. If I add them together, how many negative ABs are? I have two of them.
I see.
Okay. The formula comes from someplace. It's not just, I didn't make this thing up out of thin air. This comes from exactly just multiplying these two things out. And again, it didn't matter. These were variables. These could be whatever comes first, whatever comes second. Okay. So we can apply it maybe to this middle one here. Notice so I have two terms that are subtracted, and I'm squaring that group. So rather than writing out a chart, I could say I'm going to take the first term and square it, minus 2 times the first term times the second, and add the last term squared.
Wait, what?
Did you do that?
Where did it go to?
From the formula. The formula for if I square a binomial, I'm always going to have 2 times something in the middle. Double whatever the product is of those two things are. The reason comes from if I were to just multiply them out, you'd get the same thing. You get 2 the same numbers added together.
When did you add them?
And again, since it's minus here, this sign is minus. Okay. Well, what are these things? Well, the first thing is a y. The second term is a 7. So I'll simplify this. Y squared is just y squared. 2 times y times 7 is 14 y's. 7 squared is 49.
29.
7 times 7.
Oh.
Okay. We can get more complicated if you want. If I have maybe like a binomial here that's got more than one, it's got a coefficient and a variable. All right, we can handle that. It's still just a binomial squared, so it's still just the first term squared plus twice of the two terms multiplied together plus the second term squared. So identify what the two terms are. The first one's a 2x. The last term's a 1. So simplify them. 2x squared. What's 2x times itself? It's 4x squared. What's 2 times 2x times 1? And what's 1 squared? 1. Okay. Once you see the pattern, once you get used to doing it a couple times, it's really not as terrible as last hour told you it's going to be. Okay. It's going to fit. It's going to always fit one of these two. The only thing you need to recognize is that if it's a plus, the middle term's plus. If it's a minus, the middle term's minus. It's the only thing that ever changes. Okay. So I'd like you to quickly right now attempt these two on your own. Here. 3x plus 4 squared. That's first term squared. Plus twice the first times the second. Plus the second squared. First term. Second term. Hey, look who this is. 3x squared is 9x squared. 2 times 3 times 4 is 24 x's. 4 squared is 16.
9 squared.
Failed that one.
Wait, why would it still be squared?
Alright, the second special situation we can see is when we have what's called the sum and difference of a binomial. If you start with this setup, if I have the exact same numbers, A and B, multiplied together in two different ways. One of them, one time they're connected with addition, the second time they're connected with subtraction. If you have this setup, oh man, life is even better. Because if you were to say, do that same box multiplication, you get A plus B, A minus B, A squared minus AB plus AB minus B squared.
What?
I'm so scared. What is she saying?
If you start here, and I multiplied these two general things together, what do you notice about these two middle terms?
They're the same except one's negative.
Okay, so if I combine those like terms, what happens?
0.
They add up to nothing. So my formula is A squared minus B squared.
Wait, will that always happen?
Yes. That's the reason why I'm showing you and teaching you this pattern.
That's easy.
If you get this setup, if you get two binomials with the only difference is one's addition and one's subtraction, then they always multiply out to just be square the first term minus square the second term.
Why would it be minus?
Again, if we use the chart to multiply out, you get it's plus b times minus b, which is minus b squared. Okay. So that means if I give you these special products, like x plus 10 times x minus 10, same values, just one's connected with adding, the other's connected with subtraction. So I know it's got to fit the following mold. First term squared minus the second term squared, which is x squared minus 100. Done. Same terms. One's connected with adding, the other's connected with subtraction. It's got to fit this pattern. 2x and a 1. 2x squared is 4x squared. 1 squared is 1.
It's not hard.
Thank you for teaching.
Glad you value my teaching.
I do. I value. I don't give a value.
So then we should have first term squared minus the second term squared. X squared and a 3y.
It's just Redding's destiny.
Oh, wait.
Right? My first term, my a is x, my b is 3y. You can have whatever you want in there, as long as they fits the basic setup. If it fits that pattern, where it's the same two terms, one's adding, one's subtracting, this pattern holds.